Today, I'm just going to be walking us through a little discussion over Penko, Jordanov, and Jorg Stelling's 2018 paper, Steady State Differential Dose Response in Biological Systems. So we all know what dose response is and dose response curves. It's an old classical way of analyzing the responses in a biological system due to the addition of some agent, say like a ligand, an enzyme, or something like that. And one way that we can use this classical tool is to compare dose responses in a biological system from after and before it has been perturbed in some way, like say maybe the changing of the ligand that's in the system, a mutation, something like that. So that's exactly what the authors, Jordanov and Stelling, are interested in here, is this difference in response or differential response to non-equilibrium steady state models. And they come into this paper asking two pretty big and interesting questions, both relating to this. The first one being, how do we compare differential responses with non-standard dose response curves? And what I mean by that, we'll dive in a little bit more into this later, but just a taste, is say you have a normal dose response, like this graph I just brought up here. And let's say the red was like the reference and the blue was the perturbation. Normally you'd think that the perturbation would change it in some way. Maybe just shift it down or up, inhibit it, or make you need more dose to reach the same response or something like that. However, it's also possible that your perturbation might create a dose response that does not look like the normal sigmoid curve that you'd see. And it's not necessarily intuitive how you would compare those two graphs. Your normal methods of comparison, like looking at how they would, like their maximal effectiveness and things like that, don't necessarily work in these situations. So that's the first thing. And the second thing that they really want to look at, and what takes up the bulk of the paper itself, is they're interested in how the structure of a system, like how its topology, really affects this differential response. So more or less, how does the structure affect the function of the biological system? And to do this, you'd think normally you could probably just figure that out analytically, which is not wrong. The problem with analytically deriving sort of like how the topology might affect like the differential response after a perturbation is that in more complex systems, that can get really unwieldy. Whereas these two authors want to find a way by looking at a graphical model to easily examine the structure without doing a lot of analytical work and see if they can glean any information about the function and the differential response that way. So, and that's exactly what they do. So to give a little bit of that was a little bit of an outline, but to just give an outline about what we're going to hit in this paper. First, we're going to talk about what they call formalizing the differential response, which is really just addressing that question on how we're going to address different response curves. Then we're going to actually get into the meat and potatoes of the paper and look at the linear framework model, which is the model, the graphical model that they created. Look at how it's created, and we're going to kind of go back and look at a few graph theory methodology to get us all up to speed on everything that's going on in the model. And then we'll look at the model and how it relates to the differential response. And finally, we'll extend that basic model. So take that basic model and keep making it larger and more complex and see what we can sort of learn from it. I'm actually really excited about this paper because it ties really well into what Greg and I are working on with pharmacology using a lot of graph theory. They're using a lot of the same ideas that we're kind of using. So this whole graph theoretical model is especially interesting to me. But before we get to that, let's look at comparing dose response curves. And so I kind of went over the problem that was happening right in the intro, but this is a really good representation of what's going on, or what they want to address. And that's what happens when you have a normal dose response curve that is like sigmoidal. So let's just say this red dashed line is our reference curve. And then you have some perturbation that becomes sigmoidal. Well, we know exactly how to how to compare these two. Certain ways that we can compare them, maybe we look at the maximum effectiveness of the curve, like at a high dose. Maybe we look at the basal response when there isn't really that much of a dose at all. Really popular way to compare before and after perturbation is to look at the effective concentration. So at what concentration do you get half of your response? And that's sort of shown by like this line right here. You could also look at, sort of analogous to that, you could also look at the differential of the response. So what he calls pi r, which is really just like, say you're at the EC50 point for both of these curves. It's really just the difference in response and the differential dose, or the difference in dose between 2 points on the curve, on 2 different curves. And so those are all really easy ways that we all know how to compare curves, but none of those really correspond to something that doesn't look similar to your reference curve. Like this hormetic curve, which is just a curve where there's like, a certain dose where you get high response, but then it sort of tapers off, going either way, both lower dose and higher dose. You can't really use EC50, doesn't make any sense. None of the ways that we would normally look at that makes sense. So our authors suggest to just subdivide the curves. Basically what they say is any curve that is not monotonic, you're just going to want to subdivide it whenever the first derivative is equal to 0. So whenever there's like a local maximum or a local minimum somewhere, you're going to want to cut it and then separate it into 2 separate curves, or n separate curves, for depending on how many critical points you have. And then once you have your separate curves, then you can they're going to be monotonic curves. They're going to be curves that look really similar to, our normal dose response curves. And then we can use our same tools that we normally do on those, but, smaller. So what I'm going to do is take this figure from the supplemental information that I think outlines what they're kind of talking about really well. And right here, they visualize a segment that has already been cut. You can see before this segment, there was some sort of like local minimum to the left, and it's hitting its maximum to the right. And so inside of this segment, it looks just like, a smaller version of a dose response curve. And so the second thing would be to decide which segments you want to compare. So you can, if your dose response curves all hit the same amount of segments, so if you segment them all, 2, 3, 4 times, then it's pretty easy. You can just compare segment 1 to segment 1, segment 2 to segment 2, etc. However, if they don't have the same amount of segments, you don't really have that one-to-one map. So say you had one normal sigmoidal curve and then one like biphasic curve. Well, you'd want to compare that normal sigmoidal curve to all of the segments, so all of the monotonic curves. So you'd be comparing it to the first half of the perturbed dose response and the second half of the perturbed dose response. And then you'd just sort of get a set of relative differential comparisons, relative differential responses. After you do that, so after you decide which segments to compare, you sort of figure out where the important corresponding points are on these segments, aka once you have a segment that's monotonic, you can say, okay, well, I know where the dose of like 0 is, where the dose of basically 100%, the proportional, like full dose is, and where the EC50 for this segment is going to be. And once you know that, then you can compare the response curves like you would compare any other response curves, and you can just calculate the differentials just like you would normally. So in this situation, it's just, like I said, the difference between the differential in the, the differential in the dose, or pi d, would just be the difference between the dose of your reference curve versus the dose of your perturbed curve, and the same thing for the response. That's just the difference. Anyways, that's enough about talking about dose curves. And let's jump into the actual model. We'll come back to those. That was important, I promise. We'll come back to those equations in a little bit. But right now, let's get into creating that linear framework model that I was talking about earlier. And to do that, we're going to just go over a little bit of graph theory and a little bit of important things that we need to know that'll come up a lot in the linear framework models. And so the first thing is just how we're representing the graph. So what they are using as an example throughout the paper is a insulin receptor. So that insulin receptor, basically in this small example, has 3 different states. It has one state when it's just a receptor and nothing is bound to it. And that's going to be this vertex R. All of the vertex in our graph are states of the receptor. And then all of the edges are transitions. So a transition from R to RL, or the receptor and the receptor and a ligand, mediated by a edge with a reaction rate constant. That's also directed. So you can see which reactions are going to be reversible, which makes sense. It's reversible to go from a bound ligand to an unbound ligand, or which reactions aren't reversible. So RL being the bound ligand, and then RLP being after you have the ligand bound to the insulin receptor, it phosphorylates, not a reversible reaction. And then also the dephosphorylation and unbinding of the ligand, also not a reversible reaction. Anyways, so that's just simply the graphical representation itself. Now, I want to talk a little bit about spanning trees. So a spanning tree is a set of edges that is a subgraph of the main graph that spans the entire graph, all of the vertices. So you can kind of imagine a graph with 3 vertices. Your spanning tree would only have 2 edges because you only need 2 edges to traverse across all 3 of the vertices. And in our case, we want to focus on rooted spanning trees. And when I say rooted spanning trees, I mean a tree that is rooted in a particular vertex. So each of these spanning trees are rooted in whatever vertex is colored gray. And basically, all that means is that all of the flow of the directed edges are going towards that root somehow. And you can kind of see every spanning tree always terminates. Like if you were to start in any one vertex, it's always going to terminate at the root of the spanning tree. When you represent all of these spanning trees, you'll notice they all have a set of unique edges that have the unique reaction rate constants. If you take the product of all of those and sum them all together, you're going to get something known as the Kirchhoff polynomial. The Kirchhoff polynomial is really interesting because it's sort of, you can think of it as holding all of the information that is inside of this graph. And it relates really well to figuring out the steady state of any one of these states. So what I mean by that is you can take a fraction of the Kirchhoff polynomial of any single rooted graph. So say we root on RLP. You could take the fraction of the Kirchhoff polynomial from RLP, which is just R1 times R3, and then divide that over the entire Kirchhoff polynomial. And you're going to get the fraction of that species, RLP, that is in steady state. And then you just multiply that by the total amount of concentration of all of the receptor you have. And you can just get the concentration of that receptor in that steady state. And so to just visualize that, say we take the Kirchhoff polynomial of the rooted RLP, which is panel D, that's the graph rooted at RLP, which you can see only has one spanning tree, R1 to R3. And then we divide that over the whole thing, multiply it by xt, which xt is just representative of the total amount of receptor there is. And you'll get the concentration of their steady state.
Can I jump in, Spenser, just for a second?
Yeah, of course.
People might be interested to know that this is a classical result. It's called the Markov chain tree theorem, right? So if people doing computational probability and electrical network theory were the people that kind of came upon this 50 years ago or 60 years ago. The other thing to say is that some of these rate constants are ultimately going to be the product of a constant and a ligand concentration. When you look at this polynomial right now, it's not clear where the ligand is coming in yet, but that'll be made clear in a second.
Yeah.
The only other thing I would say is that if you look at the expression, do you see how if the numbers are rates, then you've got a product of two rates on top and a product, every term on the bottom is a product of two rates. So that's a dimensionless number, which is a probability of being in that particular state. Ultimately, if it were an equilibrium system, you would be able to take, you express that ratio there in terms of ratios of rates. So you'd be able to express this probability as a function of equilibrium constants, which is what you expect for an equilibrium system. So this is more general than the equilibrium case, but you can convert it to the equilibrium case if that's your interest. Okay, thanks, Spencer.
Yeah, of course. The last thing I want to touch on before getting to the actual model is just the graph function of deletion and contraction. And so what I mean by that is deletion and contraction is a way that we can take our original graph, so up here, and by using this technique, kind of segment our Kirchhoff polynomials in sort of two bins. One bin that only has the edge that we sort of delete and contract, and another bin that doesn't have that edge at all. That'll make sense once I sort of explain what's going on. So in E and F, we're seeing in E the deletion and in F the contraction of the edge R2. So it's pretty easy to see in E, the deletion of R2, you just get rid of it. And now you have three possible spanning trees. It's pretty easy to see. You can just have like a spanning tree of R1, R3, R3, R4, R4, R1. And then oppositely, in F, we have, oops, in F, we have an example of contraction. So basically what's going on here is we are taking the edge R2 and we are taking the edge R2 and we're taking both of the vertices that R2 is coming from and going into. And we're basically pushing those vertices together and trapping R2, like between those vertices, into this new vertice, W. How the authors explain contraction with directed graphs is that when we do that, we're going to lose the edge R1 and R3, but we keep R2 inside of this vertice right here. So the spanning tree for this, and this is kind of a simple case since it's just two vertices, but the spanning tree for this is R4 times whatever is in W, and R2 is in W. So the spanning tree is R4, R2. And if you'll notice, adding the three spanning trees that we get from the deletion and the one spanning tree that we get from the contraction of E and F, we just get the whole Kirchhoff polynomial. So doing deletion and contraction doesn't lose any information. All it does is sort of separate the information kind of around a single edge. And that's going to be really useful later. Anyway.
Spencer, can I ask a question?
Of course.
In F there, in the contraction,
Mm-hmm.
I see R4 remains. What about the edge R3? Seems like it wouldn't disappear necessarily.
Just how they defined contraction is if there was, basically you look at R2, and then any edge that's opposite R2, you just delete. It just like falls off of the graph. And then any edges coming out of the vertex that R2 comes from also get lost.
Okay, makes sense.
I guess I don't know exactly why they get lost. That's just how they defined.
If they get lost, when you contract, you're sort of making the two vertices that connect a particular edge. So when you contract an edge, you're kind of imagine those two vertices coalescing and becoming one vertex.
Mm-hmm.
And so then you can, in this case, if you contracted R1, you'd kind of have R1 and R2 hanging there as a loops off that one vertex because you've identified the start and the end, right? And loops can't be parts of spanning trees, right? A loop is never part of a spanning tree. And so that's why they disappear, because they're not part of the spanning tree, a spanning tree. And so this process of deletion and contraction, if you keep kind of doing it recursively, you delete and contract, you have two different graphs, and you take each of those, delete and contract and continue until you get sort of nothing, or objects where the spanning trees are obvious. It's essentially a recursive way of calculating all the spanning trees of the graph, attributable to Tutt, Tutte, who was a leading graph theorist.
Thank you, Greg. So now that we have a little bit, enough background, let's jump into actually looking at the model system. And this is a simple model system looking very similar to what we were looking at, except you'll know a few key differences. One, Greg already pointed out, and that's we have the dose of the ligand incorporated into R1. So the edge R1 is now dependent on whatever the dose of that ligand is. We also have red labels for R1 and R2. And that's because this model is visualizing both the reference dose response and the perturb, or the reference system and the perturb system. So why R1 and R2 are red is that's because what we're perturbing, or what we're changing, is we're changing the type of ligand in the system. So our reference system is, one certain ligand, and then our perturbed system is a separate ligand. And of course, that would change the rate constants to bind and dissociate with the receptor. And that's all it would change too, since that ligand wouldn't affect the rate of R3 or R4. Or at least we're saying it's not in this simple model. And then finally, we have one vertex that's sort of double circled, and that's just our response vertex. So that's what we're going to be measuring. Yeah, so that's like our y-axis of our response, our dose response. Anyways, so just like when we're looking at the steady state of a single concentration, we can look at the function, which is the response of this vertex. And that response, and this is a general formula, but that response is just going to be a linear combination of all of your response vertices over just everything else. And so right now we only have one response vertex, so it's kind of trivial. We don't have a sum of anything. However, you could imagine that maybe there were like 2 or 3 different response vertices, and then you sort of add them all together. The A itself is a weight. So say you wanted to weight the response vertex, like, for every 2 of one, you get 1 of the other, or something like that. Again, we only have a single vertex, so that's not really a problem. And just like the steady state, it's multiplied by all of the concentration. We can sort of break down exactly what we're doing in panel B, where the numerator is just going to be the, like we did in the last figure, the rooted vertex graph, where we root at the response vertex, which is RLP. And then we just delete and contract. And we're going to delete and contract around R1D. We're always going to delete and contract around where the dose is, because that's going to easily give us two sets of Kirchhoff polynomials, one where there's never the dose and just everything else, and then one where the dose is present in all of the parts of the polynomial. Similarly, for the denominator, instead of rooting, we're just going to delete and contract around R1D to get two graphs, two subgraphs. And from these subgraphs, we can find the Kirchhoff polynomials pretty easily. And then those will be everything that's on the denominator of our response. And just to highlight it, these are the rate reaction, the rate constants of what each Kirchhoff polynomial would be. So of course, this is R1, R3 because we have R3, and then we also have R1 sort of baked into W from the contraction. This is R4, R2, and R4, R3, and you can sort of see those spanning trees. And similarly, you can see these spanning trees here. And so basically all we do is just add K1 and K2, which is what we know as our numerator, and K3 and K4 as our denominator. And we've got the entire response as a function of the dose. And the dose, of course, since we separated the Kirchhoff polynomials based on this, based around this edge that had the dose, then we can just say the dose is only affecting K2 and K4 because those are the two sections that we contracted. And then similarly, and these are those equations that I said we were going to go back to, you can move from the response function into the dose differential and the response differential. They go through the derivation of how you get from the response function to the dose differential and response differential in the supplemental materials. I don't think I'm going to have enough time to go through them. So just to recognize that this is sort of like what you come out with at the end. The dose differential being the log of K3, K4 over K3, K4. And the alphas and betas, alpha is the reference. So like K3 alpha is K3 in the reference curve, and then K3 beta is K3 in the perturbed curve. It's interesting to note that the differential dose, the dose differential, doesn't have anything to do with K1 or K2. It's solely based off of K3 and K4. K1 and K2 kind of cancel each other out in the derivation. And actually, even more interesting, if you kind of break down what K3 and K4 are, you'll notice that you are going to have R4 on both, equally on both the top and the bottom. So that will also cancel out. So we actually come to find out just by looking at this, that the differential, the dose differential, are really only dictated by the rate constants of R1, R2, and R3, and don't have anything to do with R4. Similarly, and actually a little bit more interesting, we can look at the response differential and what's kind of dictating that. Now, the response differential has all of the terms in it, unlike the dose differential, which only had K3 and K4. However, we notice that K1 is equal to 0. That's equal to 0 because K1 isn't a spanning tree. So there's no Kirchhoff polynomial associated with it. We notice K1 is equal to 0. So that whole term kind of just disappears. And actually, super interestingly, K2 and K4, if we take a look at what K2 and K4 are, K2 is R1, R3, and K4 is R1 times R3 plus R4. In that situation, R1 is going to cancel out, leaving us just R3 over R3 plus R4. Now, the only thing that was changing in our model, the thing that we were perturbing, was a difference in ligand. And that difference in ligand was only affecting R1 and R2. Since R1 and R2 were the only things being affected, R3 and R4 are the same from the reference model and the perturbed model. So K2 alpha over K4 alpha minus K2 beta over K4 beta, that's just going to equal 0 because those are the same. So interestingly enough, without doing a lot of analytical work, we can actually see a perturbation in a system like this doesn't result in any response differential. So no matter how much you perturb this, you can change the dose differential, like its horizontal shift on the graph, but you're never going to shift it up or down, which is actually really interesting. We can sort of predict how this curve is going to move without really knowing anything about the system itself. Like we don't know any values, any rate constants or anything like that. We just sort of know the structure. And by knowing the structure, we can kind of easily make some pretty good logical guesses into what's going to happen. So now that we kind of have this model under our belt, and we know sort of how it works, let's take a look at expanding the model a little bit. So in this first expansion that we're going to do, we're just adding 2 vertices. The vertices are Ri and RLPI. The I is the receptor has been internalized. So it's been like taken into back inside of the cell. So the vertex itself is the reversible reaction between the two, but an irreversible reaction between RLPI and RI. And taking a look at this five-state model, even though it changes the entirety of the steady states and stuff like that, of course, you're adding 2 states, you're going to change the steady state, you're going to change the response of each of the vertices and stuff like that. Interestingly enough, you're actually not changing the differential response, which isn't necessarily intuitive, but we can sort of see what's going on in the model. So our new vertices that we've added and all of the new reactions that we've added between the vertices don't ever interact with what we are perturbing. So RLPI and RI and the 5 new reactions that we've added don't actually ever like couple themselves to the perturbations in R1 and R2. And you can sort of do this out. If you were to write everything out, you'd notice that everything sort of just kind of cancels back down to the differential response that we had in the first model. This is mostly due to all of the reactions being in separate prime factors. And I didn't really talk about prime factors too much because I think I'm running out of time. But a quick rundown is a prime factor or a prime graph is basically a section, a subgraph that you sort of delete and contract until you can't delete and contract it anymore. And it's I mean, it's just like a prime number. It's a piece of a graph that can't really go any smaller. And it is like, if you multiply it by another graph, you get, if you multiply that prime graph by another prime graph, you get like a larger graph that it is a subgraph of. But the reason I say that is because you'll notice none of the reactions or anything actually are part of the same prime graphs that the perturbations are a part of. So if you think the perturbations are a part of like this green prime graph right here, and this yellow one right here and right here, those never intersect with the vertices that we've added. And basically, that actually gives us a lot. It allows us to think about models in sort of groups or classes. And we can sort of take large groups of models and kind of classify them if their differential responses are equivalent, and kind of put them into these differential equivalency classes, you know, only through differential response. They're not equivalent in like steady state and stuff like that. But that means if you know a lot about a small graph, like a small simple graph, and you have a more complex model that is in the same equivalency class as that smaller, simpler model, then you actually can sort of take a lot that you know about that smaller model and also apply it to that bigger one. Which is really powerful when you're thinking about maybe designing experiments or something like that, that you can know a lot about a model without ever even really thinking about it before, because you can sort of tie it back to a previously smaller model that you've studied. Similarly, knowing that there are these certain classes, these equivalency classes, that you can sort of tie a bunch of different models to, kind of allows you to analyze a lot of different models at once. Like, let's say I was designing an experiment and I knew that when I perturbed R1 and R2, I knew that I got a differential response. However, the model that I'm looking at right now does not give me a differential response, as we've already seen. So I'd know that this model is no good. This model doesn't follow what I'm seeing experimentally. So I'd know that this model, you know, I need to rethink it. But I'd also know to not think about any model that is also in the same equivalency class. I can basically reject every model that is like similar to this model, every model that is in the same equivalency class as that model, which is a pretty, I think, interesting way to reject a bunch of like hypothetical models without really even worrying about them. Now that I've said all of that, extending our model even a little bit more, we've been working in closed systems this entire time. So let's extend it to an open system. Basically, extending it to an open system, that would mean something along the lines of looking at this, like for an insulin receptor, maybe we're looking at the insulin receptor over a long period of time. So now we're seeing the receptor like degrade and synthesize new receptors and something like that. So one question someone might ask is, where in the model is this degradation and synthesis entering? So in panel A, maybe someone would try thinking that maybe it's entering at the vertice of R. However, we can kind of see, and this is only showing one of our steps towards contraction, but we can kind of see if we contract R1 down to W here, so we're pulling RL down to R, we're going to leave ourselves with this empty vertex right here, and this was what was giving us the synthesis and degradation. Basically, what we have now is a graph that is not connected, and a graph that isn't connected can't possibly have a spanning tree that hits all of the vertices. And since it can't possibly have a spanning tree that hits all of the vertices, then its Karpov polynomial is going to be 0. However, a Karpov polynomial in a 0 of K4, if you remember, K4 finds itself in the denominator of our response differential. So that's just going to be, that's not going to make any sense. That's an undefined response differential that can't happen. So we know that this this placement must be wrong, because if we're getting like an undefined system, then it just can't sort of exist here. So then we can place it in a different spot, like maybe placing it in the logical place where it would affect receptors that have been, integrated, internalized, I mean. And then that works out pretty nicely. We get real values for K2, 3, and 4. Additionally, you'll also notice that our new addition, the open system, does not affect R1 or R2. So again, this is also in the same equivalency class as the other two models. It has the same differential, dose differential, and the same response differential of 0. So finally, I'm just going to quickly talk about extending this same model to having 2 dose edges instead of 1. And what I mean by that is adding a separate edge that adds another ligand. So now you have 2 separate edges that are being affected by the concentration of the ligand instead of just 1. This edge going from RLP to RL squared P, and that also being able to be internalized and turning into RI. So the first thing that I want to talk about is the response function of extending to a second dose edge. So adding another edge that's reliant on dose means that when you are deleting and contracting, you're going to have to do it twice. Once for your R1 and once for your R12. Basically, what you're doing is you're getting bins of Kirchhoff polynomials where one of the bins is going to be, where you've deleted both of them, and none of those Kirchhoff polynomials have anything to do with dose response. One of the bins where you've deleted one of the 2 doses, and you've contracted the other, and then you're going to have a set of Kirchhoff polynomials that are only reliant on D, and then you're going to have another set that's reliant on D squared, where you've contracted both edges, R12 and R1. You can kind of see, hopefully, that this could possibly get messy, because instead of having only 4 graphs where we have to worry about, like 4 subgraphs that we have to analyze, we now have 8 since we've added this extra dose or extra edge that's reliant on dose. Additionally, you can see as you add edges to a model like this that are reliant on dose, you're going to exponentially grow the amount of graphs that you have to analyze. So this is a neat limitation to this, even though this model is meant to kind of simplify like an analytical approach to looking at these models. It's still possible that you could also have a model like this become unwieldy. And it seems to happen quickest when you start adding too many dose edges. You can see adding like 2 more, and you're just going to have too many graphs to sort of deal with, at least by hand. Similarly, I only have a few minutes, so I'll just run through this. You can also tell, at this point in time, you can tell if a curve is going to be monotonic or biphasic. And knowing when a curve is going to be biphasic could be really helpful if you want to create a model in which, create a model in a perturbation in which you are going to see experimentally something that looks biphasic like this. Anyways, I think I should wrap up so we have time for questions. So I'm going to skip the last of this and just say in review, we've looked over a different way to compare dose responses by splitting up the dose response and sort of comparing each one to each other and getting a set of relative dose response or dose differentials. And then we've also looked at a different way of visualizing and analyzing systems using this linear framework model, which seems to be really good at determining when there might be a differential response, what models might be equivalent to each other, and when and how you can sort of reject some models because you know they aren't going to work. And yeah, that's the whole paper. Any questions, comments?